All right, so just a quick overview here. Now, we've talked about velocity and the relationship of velocity with displacement to velocity. Remember that how do we define velocity? Velocity is the rate of changing displacement, right? So if I walk over here to this point 2 meters away in 2 seconds, then and I'm moving south, because that is south, all right, or in the positive x direction, okay, because we've established that as positive x. Then 2 divided by 2 is 1 meter per second, okay? But now if I walk over here 2 meters and then I turn around and walk back 2 meters, I've walked 4 meters, okay? And let's say it took me 4 seconds, all right? Well, 4 divided by 4 is 1, but what would my average velocity be? 0. So see the big difference in speed and velocity. Speed is total distance. Velocity is change in displacement. My displacement didn't change, so I wouldn't have any velocity. Okay, all right, so what is acceleration now? Again, remember, these are annotated for you. They're annotated in the PowerPoints and the textbook, so I don't have to label every single variable. It's there for you. You can see it right here and write it down, or you can say, hey, I need to mark this page in my book and go back and write it down. I don't care how you do it. You just, however you want to do it, okay? All right, so we're on page 40 and 41, okay, and fixed to be on 42. We see this equation. Yes, you need to remember that for your formula card. If you want to annotate it, you can. But remember, this is average acceleration, not instantaneous. So notice notice here, it is a rate problem, but it is changing velocity. So if we were to take derivatives, we would take the derivative of velocity with respect to time, first order derivative, and we get acceleration. If we took the derivative with respect to displacement to get to acceleration, it's a second order derivative, okay, with respect to time, okay? You should remember that from calculus. I know they go over that in calculus, all right? So what are the units? Of course, the units are going to be what? Units for acceleration. Now, they didn't put the units on here, I don't think. No, I don't see them. Acceleration is what? Meters per second squared, or old school, and really this is how we wrote it, meters per second, because y'all, that's what it is. It is actually meters per second. It's the rate of changing velocity, okay? So I mean, it's correct to write it meters per second. Some of your old school physicists will say that too, and even some of the younger guys will do it that way too. But I remember my old physics teacher, that's the way he always said it, meters per second. Now, he said it that way every time. And that's, that's just the way but it is. That's what it is, okay? Rate of changing velocity, okay? All right, so any questions? Now, again, these PowerPoints are posted in Blackboard, okay? So if you missed something, you can go back, okay? And this is on page 40 and 41, all right? Okay, so then let's move to instantaneous velocity. Well, come on, y'all. You know it's going to be a derivative, because if instantaneous velocity is a derivative, then instantaneous acceleration has to be a derivative. So notice we're taking the derivative of velocity with respect to time, dv over dt, okay? Now, again, this all depends on our equations that we have, all right? As far as whether the acceleration is going to even exist in a derivative. Sometimes you can have constant acceleration, and we'll get to that here in a minute. And when you take that last derivative, guess what? There's no t left. Okay? And so what does that tell me? That tells me if I take that second order derivative from displacement and there's no t left in any of my variables, then that tells me that acceleration is what? 0 or constant? Okay? If we take a derivative and all that's left is a numerical value, we say that's a what? Constant, isn't it? Right? So it's constant acceleration. And you'll see what I'm talking about. We're going to work some problems next week, and I'm going to assign problems. If I don't have time to give you the actual problems I want you to do in class, I'm going to email it to you right after class, okay? So check your email, all right? And just try them. Just try working on them. I know we haven't worked any problems yet for Chapter 2, but just try working on them. We're going to work on that on Tuesday. Did I say Wednesday? I meant Tuesday, okay? We'll work on that in Tuesday in class, okay? All right, so again, the units are the same, nothing changes, but again, this is the acceleration at a given instant, whether it's at time 0, time 0.1, time 5.2 seconds, whatever the time is, okay? But it's for that given time. Now, here's a very interesting graph that you need to try to wrap your brain around, because remember we talked about velocities changing displacement, right? Okay, so if my displacement, if I'm talking about velocity and my displacement is negative, then what will my velocity be? Okay, y'all, delta x divided by delta t. If delta x is negative and I divide by time, what do I get for velocity? Negative. Okay? So what are you saying, Teach? If your velocity, if your changing displacement is negative, then guess what? Displacement now, I didn't say velocity, displacement, then guess what? Then your velocity has to be negative. Okay? It has to be. But, we can actually have negative velocity and have positive acceleration. Or we can have positive velocity and negative acceleration. And you say, well, how can that be? Well, what do you think braking a car is? You're moving forward, you're moving in a positive direction, but you slow down. The brakes are applying friction, or actually acceleration. It's through force, but it's an acceleration in the opposite direction. Okay, on the drums or the disc rotors. Most cars are now disc brakes, okay, unless you got an older one. All right, okay? So that's a good example of where velocity is positive, acceleration is negative. So here it tells you positive and increasing, getting more positive, and it tells you the direction. What about positive and decreasing? Negative, okay, so acceleration is negative, okay? And then, of course, negative and increasing, positive. So you can have negative velocity and you can have negative acceleration. Okay? You can have that. Just like you can have positive velocity and positive acceleration. Well, y'all, what do you think acceleration is? Okay? If you're continuing to increase in velocity, then you have to have positive acceleration to be increasing, to speed up. Okay? All right. And then, of course, negative and decreasing, negative particles moving in a negative x direction. Okay? All right. So, again, that's, again, common sense. But that's a good little slide, and I think this is on page, this is on page 43. Yeah. So if you want to look in your text, page 43, okay? All right, so now let's look at a few graphs, and then we're going to do our ILD here, all right? All right, so again, just like with velocity, if we take the slope of this line from one point to the next, make a straight line, and take the slope of it, then we get average acceleration, okay? Because why? Because of our slope equation. y2 minus y1 is equal to x2 minus x1, okay? Which is changing velocity divided by changing time. And remember, time's always positive. It's never negative, okay? Except on the quadratic. It can be, but it's not real, all right? We don't go backward in time, all right? All right. However, if I come in here and say, okay, well, we know our average acceleration, but I want to know what it is right there. So I need to do what? I need to do a derivative, right? Instantaneous acceleration. Or I could take the tangent of that point. Okay? I could do that. I keep mashing that other button, all right? That's why it dinged. All right, now, okay, to find that. All right, so, looking at more graphs, just like with our velocity graph, now look here. Notice what happens to acceleration right here. Notice right here it's positive. Well, how can it be positive? Well, look, y'all, y2 is less negative than y1. I didn't mean squared, I meant 2. All right? And then, of course, time is going to be positive, okay? So delta t. So look, y2, let's just say right here, is say -1, and y1 is say -3. Well, that's minus a -3, which is a +3, and so you get a what? A change that's equal to what? 2 meters per second over, and let's just say, I don't know, 2 seconds. Let's say 1 second. So we get 2 meters per second squared. Yeah, but Mr. Shields, it's in the negative region of the quadrant. Yes, it is on the y-axis, but you got to remember, y2 is less than y1, and when you stick it into your slope equation, that negative makes that y1 positive. Right? That makes sense. Okay? See, that's where we forget. We think, oh, wait a minute, that's supposed to be negative. No. You got to remember your slope, okay? So if I was to take the slope of that point right there, I would get a positive slope because it's going up. But this is interesting right here. Now, this is very interesting. Again, this is conceptual stuff now. Notice that they're telling me that the acceleration is 0. Why is it 0? I love graphs. Why is it 0? You're fixed to be doing some graphs and looking at them and analyzing them and thinking about motion. Okay? Why is it 0? Anybody? Okay. All right, very good. It reached its highest point and it stops just for a moment. Well, y'all, just for a moment is still time. Even if it's a half second, tenth of a second, whatever, it's still time. It still counts. Okay? All right. And so velocity, like you said, it stops, it's not changing, is it? When it stops, it's not changing. So what does that mean? All right. You need to familiarize, sound like Porky Pig here. All right, now. All right. So you need to familiarize yourself with these terms like constant speed, constant velocity, maximum speed. What do all these mean? All of these mean that acceleration is 0. Very, 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 very important you pay close attention to that because it'll slip by us in a problem. When constant speed, what's the acceleration? We don't even have to calculate it. 0 because it's constant speed. Okay? So terminology is important. Watch those terms. Familiarize yourself with those 3 terms: constant speed, constant velocity, maximum speed. Because if it's at maximum speed, the velocity is not changing anymore. No more acceleration. Now, likewise, how do these have negative acceleration? All right, now come on, we got to remember. If we look at, let's just say right here. All right, remember, we're going to go from here to there. All right, y1, well, we got y2 minus y1, right? Okay. So y2 is going to be more negative, let's just say negative 5, minus a minus, let's just say 1. So we get a negative 5 meters per second. No, shoot. Negative 4 meters per second divided by, say, I don't know, 2 seconds. All right. So we get a negative 2 meters per second squared. So you got to think in terms of slope calculation. Okay. All right. Okay. All right. Any questions? All right. And again, this is just on a straight line. This is just showing you motion in a straight line. All right. Notice that if the acceleration is moving in the opposite direction, it has to be slowing down. Okay. All right. Particle is instantaneously at rest. There's no velocity. Therefore, there's no acceleration. If it's not moving at all, common sense, right? All right. If it's instantaneous and it's not changing, notice not changing. Its speed is instantaneously not changing. Acceleration is 0. Okay. Same thing here, but now notice right here. If they're speeding up and moving in the same direction, they have the same sign. Okay. Again, common sense stuff. This is on page 44. Okay. All right. Acceleration versus time graph. Again, that's just kind of a why they. Well, I do see why. Taking the slope of the points. They're just showing you how we take the slope of the points, okay? All right, and again, notice the motion diagram for a particle in the previous velocity versus time graph. Okay? All right? Okay. All right, any questions? What about constant acceleration? All right, I do want to talk a little bit about this, and we're going to hit this more come Tuesday. Constant acceleration. Constant acceleration. All right. Remember from lab, oh shoot, y'all didn't do the lab. I got to remember that. Y'all are not with the other class. Okay, well we're going to do one real quick. If I drop this ball and I use a motion detector or a photo gate, preferably a motion detector, and we'll do something like this a little later on, maybe in class, or do it as a demo. And we graph the changing displacement for every time, for every second, let's say every half second, to get more data points. Okay? What do you think it's going to look like? What kind of graph do you think it's going to look like? Let's just, now watch, let's do it this way. This is displacement, it's changing displacement, and this is time interval. What do you think what do you think it would look like? If I were to take those points and graph them, what would it look like? Because basically that is demonstrating what I just demonstrated. Is it going to be a straight line or a parabola? Very good. It's going to be a parabola. It's going to look something like that right there, isn't it? Does that make sense? Because look, for every time interval, look right here, boom. All right, now let's look at the next time interval. Well, hey, it's almost doubled. Not hardly, though, not quite. Then the next time interval, it's probably gone up by a factor of 1.5, right? We'll say 1.5 from here to here, 1.5 from here to here. All right, notice when we go here, all right, notice how much we've increased by a factor of about 1.5. You seeing that? It keeps farther and farther and farther away the longer the time interval. Okay? So we get a quadratic, don't we? We get a parabolic curve. But if we come in here and we say, well, I'm going to say delta x and delta time, but I'm going to say square it. Take that same data points, what do you think the line's going to look like? Very good, straight line. Sure is. And what do you think the slope of that line is going to give me? And we got to be careful on this because we got to remember that this is a quadratic, but when we square time, we actually get a linear function. We're actually getting half of the acceleration of gravity. We plot it, but then if we take it in times 2, guess what? We get the acceleration of gravity. And you say, why half? Because of this little kinematic I told y'all to go ahead and put on your formula card right here. And you physics folks from high school probably remember this. AT squared. All right, initial displacement 0, initial velocity 0, right there. So when we graph this right here, the slope of the line is half the acceleration. You with me? You say, prove it. Take the derivative of that equation with respect to time. Take the second order derivative. And guess what you wind up with? Well, all right. What do you wind up with? Is that going to be right? Is that right? Second order derivative? Let's see. We're going to wind up with velocity. Initial velocity is equal to what? A times t? Yeah. And then acceleration is going to be equal to what? A. Right? Whoa. Okay. All right. So if we were to graph that motion right there with respect to displacement, we're going to get the parabola and then square the time and plot it. We get a straight line. We get a linear relationship. Okay? Okay. All right, any questions? So just remember, just remember that when it's constant acceleration, that means that the rate of changing velocity is what? the same. After 1 second, it's, say, 10 meters per second. Let's just round it up. After 2 seconds, it's what? 20 meters per second. After 3 seconds, it's what? 40? Is it doubling? Is that right? Okay? So it's doubling every second of time interval. That's why you do not get on top of a building, even like this building, and drop a golf ball on somebody's head. Because even though it's small, by the time it reaches the top of that person's head, it's really going to be moving on. Pretty good clip. It could hurt them and it could kill them. You know, anything bigger than that probably would kill them. You know, like a bowling ball. Well, of course a bowling ball, but, you know. You always got this baseball. Baseball might do it. People get killed by hail every year. Now, of course, it has fallen from several thousand feet. Okay, but it eventually reaches terminal velocity. But even then, that velocity is like crazy. Okay, I mean, you fall from 10,000 feet, 5,000 feet. Okay, it's going to be moving on. Okay, because once it reaches the base of the cloud and its mass is greater, high enough to where gravity, the force of gravity pulling on it overcomes the force of convection, it's coming down. And you know, a baseball-sized hail hit you in the head, it'd kill you. It'd probably kill you. Okay? People do, I'm not kidding, they die from hailstones every year. They're killed. They get it caught out in a hailstorm, big baseball-sized hail, softball-sized hail, and it'll kill you. Especially if it's heavy. I mean, just beat the fire out of you. That would be bad. That would not be a way to go. I would not want to go that way. Okay? All right. So, I mean, you think about it in terms like that, and it makes a lot of sense, I hope. Okay. All right. Okay?